let's start right away. So this workshop is a 3-day workshop. The 2 first days really gonna be lecture, exercises, a lot of things to really get the theory really right. And the 3rd day is gonna be really exciting. We're gonna have a little competition. We have a sponsor, Vast AI, who's gonna help us do a great competition by providing GPU. And we're gonna work on, you'll see, an exciting topic. But for now, we're really gonna focus on the theory. And today is kind of like a dive into this black box of how do machine learn. Like it's not the typical first course of deep learning. The typical deep course is gonna be like done by Pierre tomorrow. And today we're really just gonna step back and really understand how does it even work, like this new paradigm of having the algorithm constructed and learn from data. So maybe, yeah, actually let's try to make it a bit interactive. And also like on Zoom, I think people can also unmute themselves and speak. Okay. Yeah, would be lovely. So in 1 second. I will need, I guess, someone to
if someone can unmute and just check.
Some brave soul to speak.
Australia.
Yes, Nathan, thanks for speaking up. Perfect. So people can just listen. Oh, there's a bit of echo. Okay, good. Yeah, we don't have a system to. Is Pierre the host, or are you? I can't turn it off. There's no host, no co-host. Yes, okay. Well, guys, let's just try to be very polite, and when you want to speak, just speak up. We'll try to. We're not that many yet. But the first question is, okay, can someone be able to explain a bit what's the difference between machine learning and traditional programming? This is really the heart of this presentation. We're gonna start at a very high level. Just some ideas maybe in the room. That's fair.
In traditional programming, everything is explicitly told to the computer in terms of what steps are taken. And in machine learning, we are giving it information and it is developing some kind of understanding.
Yes. So Casper said, in traditional programming, we're really telling the computer what to do step by step. I think this is the crucial part. And then the other part is what we're gonna discover today, how we do this machine learning. Yeah, some information, some data is given to the machine. And yeah, that's really the big difference here. So very, very high level. Yes, Pierre?
You've got a message in the chat. I don't know if you can read that.
Yeah, maybe come here, Pierre. And that's going to be very helpful to have you.
Thanks. Should I stand up or just?
Yeah, show me.
Machine learning involves using mathematics, calculus, probability, along with programming.
Yes, so that's a good point too. Now we're at a very high level. We don't even describe how we do it. So here is just the difference. We can really see this function, this programming, as this little box. And we don't really care what's inside right now. We just have some input and some output. And these can be very complex objects. We're not talking about mathematical function. This can be taking complex objects like files, for example, or images. And something is transforming this input into output. The classic way is this traditional programming. Step by step, we're going to transform this input and really tell explicitly the program what we want to do. Now, machine learning is different. We're really going to show to the program some examples, some information of what we want to do. And we let this black box train develop itself to reach the right outputs. Now, we're going to stay at the high level for now. I'm going to try to go deep in the low level as we go during this presentation. But maybe at the high level, another question for you. How can we do this learning? Like, the best intuition is really given with kids. How do kids learn? What are the different ways we get information and correct with ourselves and learn about the world? Any ideas? The simplest idea, like where do kids go?
They just do something and then see what happens.
That's a very good idea. Just like kind of exploration, and they get some rewards. Maybe they fall, get some like pain. If they get some sweet stuff, they get some pleasure, and this like pleasure and pain are like one way to get reward from this like random exploration. And maybe more direct way to learn for kids. Like at school, yeah.
From parents, from
Yeah.
adults.
Or at school, yeah. So directly, we call this like supervised. So really, we show the kid what we want them to learn. And yeah, we have something.
As again saying, one way I can see making mistakes, changing the way we get the answer previously, taking into account the feedback.
Yes, yeah, that's very similar. It's like this exploration, and
Recognition.
you explore and you see if it works or if it doesn't work. So you have this signal. Or we can directly see what the parents are telling us. So maybe the parents are going to show us, okay, this is a cat, this is a dog, and we explore this word. There is a third way actually, and that's like how kids will learn is going to be just through mimicry. So they're not going to be supervised. They're just going to repeat what the parents are doing. And after like days and months, it's going to kind of understand how the word is working. Please mute yourself, guys. Thank you. So this is the very high level way of thinking about learning. We can basically divide it into two categories at this point. And so we still have our program, some inputs, some outputs. And this is describing the learning process. So one typical way, let's see. Yes, you know the output and you really correct and you compare the current output with these outputs. And this error is really your signal, your information. Another big way would be you have some kind of scoring function. You could just tell, you might not know exactly what should be the right output, but you can tell if it's a good or bad output. So the scoring function. And maybe to give you a bit like more concrete examples, yes. So typically, this would be what we call like all of the supervised learning. And typical example would be maybe we want to learn the structure of proteins, and we actually have some database about this. So we can try and correct the algorithm if it's not the right structure. But let's say for this other one, we want to have an algorithm that drives a car. I can't tell exactly how the car should drive. I can't tell exactly, oh, this should be the steering angle. But I can give it some score. I can say, oh, you're going out of the lane. You're going at the right speed. Or maybe you think about a video game. You have a direct score. And this is your signal. And sometimes it's very convenient to think about both. Now, let's go, yeah, one level below. First way, when you know the outputs, these are really, we're starting to get into the jargon. So supervised learning and self-supervised learning. Supervised learning is really bread and butter of machine learning. This is really what we start with usually. And this is what we describe. You know the outputs and it's labeled, and we're just gonna correct the output until it matches the ground truth. So you really can see that as a simple function. You have X as input, Y as output, and you correct Y until you have the right output. It's very nice, very easy to understand, but you have to understand that it's hard to get a lot of data out of this because the output has to be labeled. So maybe you have to get a lot of images of cats and dog, and a human has to label them. Another way is this self-supervised learning. Here, it's maybe a bit hard to understand yet, but you still have a known output, but it's non-labeled. It's going to be something more trivial. So a typical example is how GPT is trained. So GPT, you take just a lot of text. There's no label in text. What you can just do is take a big chunk of text, mask some of it, and ask the model to take the masked input and unmask it. So this is something we could all do. If you just mask maybe 10% of the word, you can usually fill in the gaps with the context around it. This is very convenient because you can train on so much data, so easy. And you have a few of these very like clever training techniques where this gives you access to so much data because you don't have to label it by hand. So we call it self-supervised, and it's very important in modern deep learning. Now, the other category we have is really when you don't really know the outputs. So unsupervised and reinforcement learning are two big categories here. And we won't see so much about unsupervised. Unsupervised is done a lot in classic machine learning, but not too much in the big deep learning, big data. But the idea with unsupervised learning is that there's always some pattern in the data you can discover. So typically, maybe you see this image, it's like a good example. You can see that you have some raw data points and you want to extract some clusters, some groups. And here the signal is typically going to be, are your groups well separated? We see right away with our eyes that this group looks very legit, they look really good. If the algorithm decided to do like some weird putting everything together or some weird subgroup, we could tell it's good or bad. So you can't tell exactly what should be a cluster, but you can still say it's good or bad clustering. A big branch in deep learning is also called reinforcement learning, and that's the typical example with the car of the video game I gave you. The difference is a bit more subtle. You still have some signal to tell you how good it is. The difference is really about the framework. These are usually the framework of an agent interacting in an environment. So very much used in robotics and video games as two typical examples. And the agent is taking an action. So here the deep learning model is really just outputting actions and receiving some reward from the environment. Typical is in the like maybe a simple video game like Tetris, you directly take the score and this is your reward, this is your information. So that's a very high level, and that's like how we have different ways to gather information and guide the program to learn. Next, we're gonna like dive a bit more in really how we do it. And the first step is gonna be what's gonna be the structure of our deep learning algorithm. So we saw these kind of gears inside the program. Like we wanna make it a bit more formal. We wanna have some structure for our algorithm to train on. And this is what's called parameterization. This is basically our framework. So if you think about traditional programming, the typical framework is just going to be text. It's your programming language. This is how you construct your program. Here we need something else, and we're going to use some model. So what is a model? It can be a lot of things. You may be used to scientific model, simple equations. These are models. It's a way to represent reality. It's a way to compress reality in a finite set of parameters. And we do this because we can reason about it, and we can also put it in the computer and run some simulation, do some programming around. One very important point, especially in the context of deep learning, is that they don't need to have an intuitive meaning. So you might be used, I don't know, like Newton's gravity, law of gravity. These are very intuitive models. You have like the mass of the object, the mass of the second object, the distance between the two, and the gravity constant. And all of these dictate how strong is the gravity. Sometimes the models will be like very abstract, just some numbers. And when you have the right numbers, it gives the right outputs, but it's hard to really give a meaning. And we have those big models, especially like the big deep learning model, are very hard to get an intuition and an understanding of what they're really doing. But they have a really nice property, so we're gonna explore those mainly today. The first example, to really get a grasp of what is a good model, is the typical problem of line fitting, regression in general. So say you're a data scientist and you get those data points, some X, some Y. It could be anything. It could be like, I don't know, some social economic data you gathered. X is the input, Y is the output, and your task is to get a model, so then you can query Y at any X. and maybe extrapolate. So for bounds outside of 0, 10, you can kind of predict how this is gonna behave. So maybe it all done something similar to that. I'm kind of curious, what are the typical things you could do? Like just to try, like the most simplest way to model this data.
You can pass like a straight line graph.
Straight line, yes, that would be the typical thing. Like linear regression, basically. Well, yeah, I chose those data because this is not gonna work so well, linear regression, as you can see, but it's definitely a good start.
You do SVM maybe?
SVM, so support vector machine. Yeah, so support vector machine is already a machine learning technique, and it's very interesting. It's already a bit advanced, but that's definitely something we could do. What did you say about regression? Logistic regression? Definitely. These are like all like ready to use algorithm you can try in SciPy, these kind of things. In our case, what we're gonna try is think about a simple model that we can fit on this. And maybe just to also go back to what we had before. This problem, is it more like supervised or unsupervised?
I mean, since it's unlabeled, I think it's not supervised.
Unsupervised?
Since it's unlabeled, is it a labeled data or?
So you have X and you have Y.
Oh, wow, so it should be supervised.
Exactly.
Yes.
Here we have the output. It's very clear. So it's a type of supervised output. So what we're gonna try is a simple polynomial model. So here the parameters are the polynomial coefficient. So you might remember you have typically B, A1, A2, and you have those powers of the polynomial. And as you get more and more numbers, your model is gonna get more and more complex. So linear regression is a type of polynomial fitting. And this is actually what we have on the plot right now. Super simple, straight line. You just have two parameters to fit. And as you can see, it's pretty bad fit, but it's a start. And the great thing about this, we can just keep adding more parameters until it's more and more. So let's just try that with now 3 parameters. So you have this green line. This is like a quadratic line, and it's not too bad, but it's still pretty bad actually. So let's just keep going. And actually, if you add like all the 5, so now we have 5 parameters in our model, it's a pretty good fit. So you see this like purple line. It's kind of doing a funky shape at the end. We don't really know if it's correct, but looks pretty good. To give you an idea what is the real data, this is the red line. This is like this exponential combination of exponential and polynomials. That is actually very close to our polynomial. Now, there are a few problems. Like the biggest problem is with this little part, and it's going to be a common problem in machine learning. Clearly, the real function is going up and our model is just going down. So as we move out of domain where we don't have data, it's always a bet what's going to happen. But inside the data, what's really important is the fit is really good, and we could have like an even better fit if we kept adding more parameters. So really the big takeaway is you don't need to know the real model to get a good fit. And this is like the key point in deep learning. Our models are completely abstract. They don't mean anything. But still, we can get very, very good fit, very good results. And so they're really useful to use. Yes, that's what I said. More complex the model is, better fit the data. It doesn't have to be the real one. Okay, let's try a second example to get another idea of the model. So you get also this data. You don't really know what it is. Say it could be anything, some X, some Y. You receive both. Maybe, I don't know, this could be like X could be like age, and Y is like the wealth. It's like representing a population. Each data point is one person. And maybe you see that in this population, you have pretty clearly 3 clusters of people, right? Like young people and old people, different wealth. Your goal is to kind of cluster these, to find regions. And by eye, we can hope that the algorithm will give us like 3 nice clusters. So then in the end, once this is correctly modeled, you can come with a new person, so new data points, and you can directly tell in which of the 3 groups it belongs. That's the goal. Is it supervised or unsupervised? New question.
Unsupervised.
Unsupervised, what do people think? Is it clear for everyone that it's unsupervised? Yeah. Here, y is not the output. The input is x, y. And the output is what cluster is this? And this output is not well defined now. Okay. We need a model, and a good way to model this is usually with mixture of Gaussians. So each cluster is going to be one Gaussian. And the Gaussian is going to represent kind of the spread, the variance of each cluster. So that's the formulation. And here's the same. Our model is just composed of a few sets of parameters. For each Gaussian is going to be the mean, so the center of the Gaussian, and sigma is like the variance, the spread in x, in y, and the orientation of the spread. So if we start with just one Gaussian, it's just going to try to capture all data points, and you see it makes a lot of sense. The point is in the middle, and it kind of spreads and tilts that way. K-1 is completely useless for clustering. But if we keep adding more, as we did before, we can see how the algorithm behaves. And with 2 clusters, we can see it nicely captures those 2 things. But by eyes, we can say this is not correct. And you can have like a few metric that says this is not correct. So we should keep going. If you add 3 Gaussians, you have this very nice clustering results where all data points are well captured. But you might not know it's KU of 3, so you might keep going. So you might like way more. And you see here we start to have like some overfitting, some overclustering, where some data points are not well separated into clusters. Same, there's nice metrics of separability, and to really show that this current results is not correct. Basically, at this point, we use simple models, and we're gonna actually try those in the exercise. So models, you can just write pen and papers and work with them. Now we're here to do deep learning, and we're gonna very quickly move to way bigger models. So we need something that's scaled up. Like these architecture can be nice for maybe up to a few thousand, few hundred, few thousand parameters. We want to go much higher. You maybe I've heard about like billions of parameters in GPT. At some point, that's what we want to reach. In this workshop, we will reach up to a few millions parameters. So people have thought about this, how to scale this up. And this is your typical neural network image. And you might have seen this before. The idea is really, the input is here on the left. So it can be not just one number like we had before, it can be a list of all of things you want to put as the input of your model. And the output is here, same, parameterized as a vector. And really the weight of the model is going to be those arrows. So you see at each step, for example, this little intermediary value is going to be the combination of all of the values of the inputs weighted by this arrow. So the parameter of the model is going to be the weight of this arrow, and we can have many of these layers. Mathematically speaking, the formulation is this one, AX plus B. So A is really this matrix of weight, combining this input to get all of this output at once. It's a way to parallel process the whole layer into one operation. And B is just a bias. We'll dive more into this later. But just to show that this is nice, very easy to compute, and very efficient. So you can scale this up and have many, many layers. This is the most basic one. You can actually go really, really deep into this and really, really complex. So this is a high-level schematic of AlphaStar. So this was a program developed to play the game StarCraft. So I think basically the program will receive this image and some information about the game, and we try to really play this game, which is a really complex game, really made for humans. So you see all of those blocks are basically some kind of neural network like this, but really arranged in very complex ways. So you can get really, really creative with that. So maybe to conclude on parameterization, first thing, any problem, even complex thing like playing a video game, can be parameterized with the right model. And the more precision, the more complex the problem, the more parameters we need. This is all very intuitive. And what we're interested in is like those very abstract models. So we have to keep this in mind. They're going to be like very much like black box. Now, this is chapter optimization. Maybe we'll take like a little break just to have any questions. I don't know if in the audience there are questions in the chats or here in the group. Now is the time to speak. Because this chapter is going to be a bit more dense. So
Can I pose a question? Just
yes.
to make sure we got that. So how are we defining and differentiating supervised and unsupervised learning?
So you're showing it to,
Anyone?
I think supervised learning, just like this. If you want to do supervised learning, you need to have labeled data for that. And when you don't do when you're doing unsupervised learning, you don't really know the outcome. You have like a set of data, and you're telling the machine to kind of cluster this data into groups. It is like you have a girl, boy, you have like a cat, dog, or maybe a rat. You know these things are not labeled. You kind of tell the model, are you able to cluster and differentiate without giving this label, which is a cat, which is a dog, which is a rat?
Yeah.
So, well, when you talk about supervised learning, you have an outcome, you have like a set of data that is labeled. Maybe you have like a data set of biopsy, or maybe a cell, a kind of cell, different kind of cell. You can say this is a blood cell, this is a different kind of cell that is labeled. So now the machine is going to learn with the data at a different label. So that's like different.
Yeah, I think that's a great idea.
Thank you.
Yeah, really knowing the outputs. It's about is it convenient to label it, and is it doable even? I think the video game example is a typical one. Like very often you don't even know what the machine should do, and sometimes you actually expect the machine to do better than you. Robotics is especially the case. Robotics, you're gonna drive, maybe imagine like a legged robot has to like give very fast commands, like hundreds of hertz, hundreds of commands per second. And as a human, I have no idea how exactly the knee of the robot should be positioned in time. But I can tell if it's falling, if it's going in the right speed direction, I can tell if it's good or not. This is unsupervised, like unlabeled. Okay, guys, we're supposed to do a little break, but we're a bit late, so we're gonna try to move on. Are there any other big questions before we start? Because it's gonna be more complex, definitely. All right, optimization. Let's do it. So until now, I just gave you an optimized model. I just show you a model like the mixture of Gaussian or the polynomials, and I just tell you, oh, here it is. It's trained, it's fitted. It's actually a big area of study. How we take this whole machine learning thing and transform it into a trained model. We start with random weights, and we need a separate algorithm, the optimizer, that's gonna train it. To maybe make it a bit more concrete, we'll go back to the regression problem. Yeah, someone speaking? Okay. So let's go back to the regression problem. You have this data point. This time, as you can see, it's a nice line. We make it simpler. You need to fit a line. We'll go back to the polynomials, and you decide to take ax plus b, a simple line. How do you find this? Like, actually, I'm curious about your idea. Imagine you don't really have any SciPy, any fancy Python library. You just have this data. And you want to find x plus b, so the slope of the line and the offsets. What would be like the simplest method to get this? Simplest and most dumb method, honestly.
What's on the line?
2 points. Yeah, actually, that's a very good idea. I didn't think about that. You guys, yeah, you take 2 random points on the line, and that's you do like the classic formulas. Okay, but say you want to use all data points.
It uses linear algebra from Fahad Alikan.
Yeah, there are some methods actually. Linear regression is written pretty simple in algebra, and you have some formula that can give you this.
2 points now, why you spread on me?
That's probably a better idea. 2 points are far away. Now, say you want to use all data points, and you don't know so much about linear algebra. You just want to brute force this. You just want to use your Python skills to like crunch the data. You just have to find 2 numbers, A and B.
That
Mean
is
square.
used by the bias and,
Yeah.
Fahad is writing mean squared error minimization.
This is a great idea, but it's way too fancy for me. One way that is just very simple is grid search. You have just 2 parameters to find. You can just try. Like, you look at the data, it's 2D, you can look it by hand, and you can check, okay, the offset is probably around something like 5 or 4, and the slope is maybe, I don't know, times 3, times 4, something like this. So maybe you start with your best guess, and you just try a lot of numbers, but it's just 2 numbers. The computer can try so many combinations. So let's try that actually. You start with A equals 0, B equals 0. So now we're gonna have a separate plot. And this is basically gonna give you the cost, the loss, the information about your current model, how well trained it is. So what we're gonna use as a cost function right now is, this is mean squared error actually. So for each data point, how far are we to our model? And we're gonna do the squared error. So either we're positive or negative, we still get like a positive error in the end. And we're gonna do the average for all data points. So right now we have a pretty bad model, and we can just keep searching, changing the slope, and you see it's a bit better. Now the color is a bit lower. We're trying to go like basically to cost of 0. And just keep going with trying a lot of different slopes, different offsets. And it's actually pretty fast to just run the numbers on the computer and try a lot of options. And you're gonna get this beautiful map. So just to make sure we're on the same page, this is the map of parameters. It's gonna start to be a bit confusing right now between values and parameters. So every time you see this slide, I'm like try to rethink about where the values, where the parameters. This is really the value, input and outputs of the data you're using. These is like the parameters. Once they train, the parameters are fixed. The values, they're gonna keep changing. Whenever you need them, you're gonna have new values. So here it's a map of the parameters, and you see there is like a combination of A and B that has like a really, really good score. You can also see it in 3D. What's the big limitation of this? Why is it not gonna work in the long run?
The lowest error.
Lowest error? To find it, the lowest error? What do you mean exactly by the lowest error?
It's asking about like the process itself, so like grid search,
Yeah, yes.
using it to find like the A or the B for the model.
Like, I mean, the lines fitting, so if it's the lightest color, it has the lowest error and something above the.
That's the goal, yes.
Yeah.
Now the question is, why is it not gonna work in the long run to use this method of grid search? What's the big limitation?
There could be multiple numbers.
There could be, but actually this method, you're just trying everything. So if there are like a few local minima, you can just compare them, and there's always gonna be one that is at least slightly smaller than the other. So actually this method is pretty good to handle that. So the big issue, what's the big issue here?
Because you're working with, there's like too much computation to do.
Yes, especially in what regime? When will it be not working anymore?
When, I mean, sorry, if I'm not trying to digress a little. Like if you're doing like matrix multiplication, there's like too much, but calculation you have to do with all of the things. So you have to find like a way to automate the process.
Yes. But I still want to say that if you have just two parameters, honestly, you can do this. If it's a simple problem, you just want to get things done quickly, this works. The big issue is scaling up. We're trying to go to millions of parameters. We can't do research in a million dimensional space. Way too slow. We're gonna try learning about a better algorithm that's called gradient descent. And it's gonna be a bit more interesting problem. So here again, yeah, there's something in the chat.
Yeah, Fahad said about bias trade-off. Variance trade-off, sorry.
Yes, but at this point, it's not so much about the model. It's really about the optimization. How do you find the best parameters? So here, we have to say, we fix the model. Maybe we have too many parameters and we're overfitting, but it's okay. Right now, we're just trying to find the best model for these parameters. A new plot. This is a plot of parameters again. Let's be careful. This is not some data you receive. So imagine you have a model and it's just one parameter. This parameter from -5 to 25. And it's similar to the plot we had before, but now in one dimension. So we just wanted to see the costs over this parameter. So you could do research here, right? All of these values. This is basically what I did today. But in the more general case, you don't have this whole line. To get this line, you have to try the model for all of those values, which can be very expensive. What you usually have is you're like somewhere in this map. You start at a random points and you get a value. This is your height. And the goal is to get to the lowest value, but you have no idea where it is and you don't see around you. It's very similar to the problem where you're like lost in the mountain hiking and it's very foggy around you. You can't see much. And you try to go to the village down in the valley. You can't really just look around. Every time you look, it's expensive. It's some computation to run. So the simplest thing you can do if you want to go down is you're gonna feel where is down locally. You're gonna do a little step forwards, little step backward. You're gonna feel where it's going down and you just take a step in the downward direction. Super simple. And actually, it works super well because most functions behave really well. And if you do this, you can then repeat it. You feel where is the downward direction, you go in the downward direction, and then you repeat. The formulation mathematically is this one. We're gonna start digging the math. So let's look a bit at the equation. Theta is your parameter, and it can be a giant list of parameters, a million parameters if you want. Here we just have one, going from -5 to 25. And we see theta plus is the new parameter, the new better estimation of the parameter. And we're gonna keep iterating with this formula until theta plus reach the optimal one. How do we update it? Well, we have this term, alpha times this weird thing. This is the gradient of the loss with respect to theta. This, we're really gonna dive into it. It's critical to really understand it. Basically, in our case here, this represents the direction of the slope of the graph. And if you do minus this, is basically the direction of downwards. This says when I change a bit theta, so my parameter here, how much the cost, the loss changes. And the great thing about this is it really applies to whatever dimension you want. So in a very high dimensional space, you're gonna have for each dimension, each of the parameter, a direction that points you to where the cost is decreasing, which is your goal. And alpha is just a little step. It's just a number to say that you're gonna take a little step to make it stable. So at the high level, this is what you do. You're this little guy taking little steps, and most of the time it works really well. Like it's gonna behave nicely and you're gonna reach the minimum. What is the limitation of this algorithm, both in terms of computation and correctness of the solution?
You have to take many steps to reach the minimum. So.
Yes, that's taking some time. It's still better than doing research. Like, if we check the 2D map, this is so many steps. And especially like exploring areas that are really, really bad. Here, really trying to explore the area that are good. We go in the direction that is getting better. But it's still many steps. What is one clear problem that we have in this graph? Like we started at this point.
You might get stuck somewhere where everywhere around you is technically worse, but you're not actually in the best position, like if
Yes.
it's like a local minimum or something like that.
Yeah.
Local minimum is typically something we're going to talk about, and it's very clear on this graph. I could have started here and end up probably here, which is great. One way when you have a small problem like this is just to restart a few times. Yeah, there is.
Yeah, exactly. Like Abulton was saying, what if there are multiple minimums, which we have here? And then I was saying it may enter a valley and never exits if the valley has a local lower cost.
Yeah, definitely. So the good news is actually this is less and less a problem as you have like a higher dimension. This is 1D, so we can very clearly see this nice trap. Now think about 2D, like you read this valley. Now you need both direction, left and right, forward and backwards to go up to really create this little trap, this little local minimum. Imagine now you have 1 million dimensions. To really create a nice trap for the algorithm, you need all of the dimensions to all go up, right? So it's less and less of a problem for once when you scale this up. And usually, even really big models learn really well with this method. There is a slight issue in the computation that we have here. How did we get the gradient? How did we get the direction where to go? We still need to do one step, maybe a second step, and feel around. So that's maybe 1 or 2 passes, forward pass of the model. This can be expensive. And this was just for 1 dimension. In theory, you want to feel all dimensions. You want to test all of them, maybe individually, to really make sure where to go. If you have 1 million parameters, it's roughly 1 million passes. Totally not doable, especially because we have to repeat it. It works well for kind of mid-range models, like maybe tens, a few hundreds parameters. So you can keep this in mind. What we're gonna do is we're gonna try to explore a way to get this direction of downward, like directly, like explicitly from the model. So this is gonna be the last part of the presentation, the last like math-based presentation. There is another message. Okay, sorry. I don't know if you guys remember a bit from calculus, what is gradients or derivative of functions. We're gonna try to go back a bit into this. Who actually in the room doesn't remember much about this?
Who in the room
Who doesn't?
definitely remembers everything they learned?
We can formulate like this. Yeah, who remembers very well how like derivation and gradient works? Yeah, a few. Nice. We're gonna go over this again, especially the practical part. So we can do gradient descent by hand, pen and paper. So the way it's presented usually, gradient is the vector of steepest increase. So vector is a direction. And it's the local slope, indeed. So in 1D, it's very easy to visualize. So here you have a graph. It's a straight line. The slope is constant, always going up. And you see this polynomial, this quadratic function. You have the slope that kind of changes, like negative to positive. So this is all pretty clear. Say you have this graph, y equal 4x. So maybe this is your loss function actually. And x is your parameter. Now, what is the slope of y with respect to x? We start simple. 4, okay, thank you. What is the slope of x squared? Okay, nice. I see everyone remember the formulas. This is super precious. Imagine this is a model. We did one pass, we have the slope. We don't need to do 1 million pass. This is critical. We now just need to kind of scale this to any model. So we saw that.
Sorry, can I ask a question?
Yeah.
So when you're taking the slope of that line, I thought that only meant like you're getting the derivative for that one parameter. What do you still have to do it for all the other parameters? So it's like the same like computational cost, or are you taking the slope of like the shape of the entire data?
Usually you get, it's a good question. In practice, what's gonna happen is you get a nice expression that still depends on all the parameters. You build this kind of graph. All of the parameters are connected, and the same way you have one expression of the loss function with respect to all the parameters, you're gonna get an expression of the slope of the loss with respect to all the parameters. So then you do a kind of a forward pass of the slope, right? It's still much more efficient. It takes some time still, but much better. Yeah, one thing we have to keep in mind. The gradient is always with respect to something. It's really important in deep learning. We tend to present just the gradient as one number, the slope. We have to think it is with respect to here, in our case, the parameters. And usually we're interested in how the loss changes with respect to the parameters. So it's always two things. And very important when you start to have like a lot of numbers in your expression and a lot of like letters in your big equation. You want to see what is the slope with respect to what. I give you little cheat sheets in case you don't remember it, because we're gonna need some of this. It's very heavy, you don't need to remember that, but yeah, it can be useful. Derivative of a constant with respect to x is 0. So you see here, what is the derivative of c with respect to x? It's 0. But what is the derivative of c with respect to c? Not the same. Actually, anyone knows the answer? What is the derivative of c with respect to c? 1. Is this 1? Okay. And you have like big formulas, you really have to keep this in mind. Everyone is like pretty familiar with all of this, so it's gonna be quite helpful. So yeah, you have a few basic functions and you can compose this function. So at the end, any big model you have can be very well differentiated. This, if you remember the neural network, AX plus B, this big matrix multiplication, you also use the same kind of rules. It's basically this model. C would be the big matrix A. Let's try to do it together once before you have to do it yourself in the exercises. So again, we have those data points and you want to fit a line AX plus B. So you have to find A and B. Actually, I just gave you the answer of the first question. So model is going to be AX and B. You have to find two parameters. What's the loss? Or actually, any loss? Squared error, yes. How does it work exactly?
You are like
the distance from the point to the line, or the closest distance from the point to the line, and then squared, and then, what is it, you say mean sum squared or whatever it is?
Yeah.
And then that's the loss, where like 0 would be perfect.
Yeah.
And that's what we're doing. Sorry to jump the gun.
Yes, it's good. You always have to ask this question, really, especially for the exercise. What's my model? What's my loss? That's a good framework. So model actually, yeah, actually we're just gonna do AX today. Otherwise it's gonna be a bit too messy. So your model is just A, basically. You just have to find one parameter. And the loss, yeah, let's do mean square. So you do a pass of your model and you compare it with the ground truth Y. Bit more complicated, what's the gradient? So L of A, we need to find this gradient. Gradient of L with respect to A. Yeah, I'm not gonna ask you to exactly do it orally, but this kind of thing we're gonna have to do pen and paper. Would you roughly know how to do this? Like, do the derivative of this whole expression? I'm gonna give you all of it, and we're just gonna go through this step by step. The good thing with the gradient is like it's a linear operator. So the gradient of this whole expression is actually like the gradient of an average is the average of the gradients. Like super important. Otherwise, that would be really difficult. So the gradient operator moves inside. Now we just need to do the gradient of this function. That is not too complicated. If you remember, like from here to here, if you remember the composition rules, we basically have the function squared is one function that's taking as input this whole function x minus y. And the composition rule gives you that you do the derivative of u squared. It's like 2 times what's inside times the derivative of what's inside. And what is the derivative of x minus y? Here, that's interesting. You have basically 3 different letters, and we just do the derivative with respect to a. So this is x. X is basically kind of like the slope of a. And you have that expression. If you combine all of this together, you have the full gradient descent algorithm that you can do by hand. You start with some number that looks pretty good. You do the loss, you compute the gradient of the loss, and you do a little updates, and you repeat until you have some nice convergence. So we're gonna start this, and that's gonna be basically next exercise. One conclusion optimization, we saw basically 3 methods. The 2 big methods would be just this kind of random search, and the other method would be you try to go in the direction of best improvement, and a lot of methods like fall into this. And gradient descent is a very commonly used, especially used in deep learning. This numerical estimation of gradients is when you check around, you probe the loss around you locally to find an estimation of the gradient. And analytical gradient is when you can compute the slope directly from your model, which is much faster usually, but a bit harder. Fortunately, lots of libraries to do all of this automatically. Today, we're not going to use so much of this, but tomorrow we'll do that. And that's about it. This is general, like, recap slide. We saw what's inside the model, those parameters, those parameterization. We saw how we can get some information about the current performance and feedback this to the machine learning to train it. And this is the general framework of the machine learning. Do we have any question? Good. I think, yeah.
Could you go back to the slide with the 4 steps?
Yeah. Yeah, this is going to be
Can we get a
helpful.
show of hands for who feels very confident in their understanding of this? Are there any questions about any of these steps? These are going to be important to understand.
So wait, actually, I do have a question.
Yeah.
What's the small L for?
Oh, yeah, so this one.
For updating the parameter.
Yeah, sorry, because we call it A before, but A is now taken. So L is LR, actually learning rates, which is how it's defined in modern deep learning framework. So it's a small step, the step size, basically. we're gonna dig into the exercise. I feel like most people actually know pretty well all of this. It's good to see. So we're gonna try the exercises now and just ask questions. It's gonna be much clearer once we read to it. I'm gonna keep this now. I think we're just gonna take 10-15 minute break, maybe get some foods. And I'm gonna send you guys the slides. And we're gonna start the exercises. All right. See you. Yeah, maybe at 10:20 here. You just have a few falling. So you have the altitude of this object over time. So here T, you have like 5 timestamps and the 5 altitudes over time. So it's like a nice classic quadratic line. And we need to find the gravitational constants, and you'll be able to check if it's correct at the end. Basically, yeah, you can just go over the different points. The start is really just application of the slides, so the different steps, trying to write the loss, then write the gradient of the loss. It's going to be very similar to what we had on the slides, but here, because the model is a bit different, yeah, the loss is going to be a bit different too. And then we're going to use this in Python. We're going to have a little, you can just basically implement the steps in Python to do all of the steps, maybe 100 steps in the software. So just start with that, and when you have any questions, just raise your hand and we'll come to you. Guys, we're gonna do a small update to be sure that everyone is on board, and we'll try to move on to the rest. So who in the room has been doing the first part? Who is good with the loss function? A few people missing this part.
It doesn't have a loss function there.
Okay. How about 2? Who doesn't have the gradient of the loss function yet?
Your loss function, you don't have to do anything.
Okay. You're still explaining on this. I'm gonna write it on board so we move on, because we have basically half an hour to also implement in Python. I think it's more to go over this. So I'm gonna show you a bit the results, and you can keep talking about this. Pierre, if I write on this, can we see it well on the Zoom? Okay, it's gonna be a bit easier. Okay, perfect. So the first question is the loss function. We have this model. And we want to find the parameter G, the gravity constant. We have a bunch of data points, X and Y's. What is a typical loss function? I think we mentioned it many times in the slide, right?
Square.
Mean square error. This is great. So how do you do it? So now it's the loss with respect to G. Everything is going to be with respect to G. And it's going to be the mean of all of the prediction of your model. So this is going to be altitudes predicted by the model. We start with a random G, and we can try with any G. And we compare this model G with respect to the real altitude. And actually, let's not use X and Y, let's really use their names. So T and H we have, and G we want to find. So everything is known here when you fix a G. That's question 1, basically. Question 2 is, we want a gradient. So more specifically, we want the gradient with respect to G. So how much change of G's impacts the loss. And it's gonna follow similar derivation as the slides, but the model is a bit different. So the gradient of this whole thing, here the mean is basically a sum of all elements. The big trick is that the gradient is linear. So the gradient of the mean is the mean of the gradient. It's the same. So when we do the gradient of the whole thing, we can actually also just write it as the mean of the gradient of the inside. And now, the bit tricky part. It's similar to the slides. What's the gradient of a function squared? There is this like composition rule. Yeah, Casper?
2 times the derivative of the function.
It's two, almost, it's similar. There are 3 terms. It's like, what is the derivative of x squared?
Yeah, 2x.
It's 2x. When you do derivative of function squared, it's 2 times the function times the derivative of this function. So here where the function is this one. So more precisely, we're gonna have the mean of the derivative of, well, it's the way we set it would be like 2 times the function itself, gt squared minus h, times the derivative of this. And what is the derivative of this with respect to g? Is it clear for everyone that it's t squared? It's a bit confusing, you have so many letters. This is why this is super important with differentiation with respect to g. So what is the slope? What is the coefficient of g? Is indeed t squared. T squared is scaling up g and it's gonna scale up the gradient too. So here, what is the gradient of h with respect to g? It's 0 because h does not depend on g. H has no impacts. It's actually, that's about it, I think. Let's check on the solution. So, I can find my mouse. Yes. So let's open the solution. I will send the collab in a few hours to give you some times. But yeah, this is model GT squared, this is the loss. So here the mean is really shown as the sum divided by the number of elements. That's how you have to program it.
You might want to zoom in.
Hmm?
Zoom in a little bit.
Oh, you don't see, can we zoom in? Oh yeah, we can zoom in. Yeah. So the mean is gonna be implemented as, you're gonna compute this term for all elements, sum it, then divide by n, classic average. And in practice, the loss is just gt squared minus the real h. So would everyone know how to implement this equation? You have all of the t's, it's a list, 5 elements, you have all of the h, and you can start with some random g, and n is just the number of elements, here it's 5. So would everyone know how to code it in Python, or would someone who wouldn't feel confident doing it in Python? Here you can describe it as a function, like def of your function in Python. The second part is the gradients. So actually the whole gradient descent equation is as usual. So we're gonna iterate on g, this is our parameter. And we start with a random g, and then we update it with this rule. And what we really want to find is this gradient of the loss with respect to g, and this is what we found here. It's actually, yeah, this is correct. 2 times g t squared minus h times t squared. Same, it looks like a big equation, but we have everything. T is a list of times, we have it. H, the list of altitude, we have it. T again, you put everything together, sum divided by n. Are there any question on the derivation of the loss and the gradient of the loss?
What do you say?
Are there questions around the math part? Like, how do we get this equation? Like, let's use that.
I think in the question we had a number of n. We had an n, but
N is basically the number of data points we have. Yeah, it's an average. So n here is 5. We have 5 data points. So basically, these two equations, the loss and the gradient of the loss, are going to be repeatedly computed over many iterations until we converge. And that's the next step. So we have around half an hour before we go to John Per's talk to implement this. At least try to have the loss and the gradient of the loss programmed. So you can input whatever G and you get the real value of the loss. So both of these should be one scalar value. And then try to implement the algorithm. So here you start with a random G, maybe just start with G equals 0 or 10, whatever. And do a few of these iterations. Yes?
In this case, LR is the learning rate, so is
Yeah.
that like a single number?
Very correct, yes. Good point.
So
Here,
like-
this equation,
So like the step size.
it is a step size. And in this equation, everything is a number. As we move to more complex models with more parameters, what's going to change? G is going to be a vector, all of our parameters. And gradient is also going to be a vector. One direction per parameter. Okay, I won't speak too much more to give you a bit of time. Yes?
Are we using the one LR value or anyone can choose?
Yes. LR, maybe you could start with maybe 0.1 or 0.001, something like this, a small value. The smallest value you get, the more stable. So start with something small. And as long as you see it decreasing, you're in the right direction. If the loss is decreasing at each direction, you're doing something good. If not, try to reduce learning rate or check if you have any bug. Okay, I'll let you work on Zoom. Don't hesitate to ask any questions. We have Pierre who is listening to you guys.
Yeah, so I hope you hear me well. So this is a really good question, Abeljan, that you mentioned. For now, like just set the learning rate at something like that's a small and standard, like 0.1. 0.1 should do. But yeah, like really good question. You can also like feel free to experiment on this. And what you can basically gonna see is that like you're converging much faster or much lower, or sometimes you get stuck if your learning rate is too high. So yeah, but feel free to have a look and experiment.
Quickly check the solution together. So I think most of you like solve the problem. It's all about like doing some nice plots and a little optimization of your code. So let's look at it together. You should have something very similar to what I have. So the data T and H, input output, I put them in NumPy array, makes everything runs faster because we can parallel process it. So if you don't know NumPy, it's nice to know. It's nice to dig a bit into it. PyTorch is going to have a very similar interface. And it allows to do computation like this, where the whole expression can be computed at once in one line. But basically, it shows something similar. We initialize G, so randomly, small learning rates. Yeah, always try something like this. Actually, usually I would start with something even smaller for a new problem. It's always better to start smaller to avoid having like instabilities. And then, basically we compute the loss first step. You see we can compute it at once with np.min. The gradients same. In one pass we can compute it, so it's all very efficient. And then the usual gradient step. So this is basically G equal G minus learning rate times the gradient. So all of these are just scalar values, but remember that usually we would have vectors here. So the gradient would be a vector of size number of parameters. G would be all of your parameters, and learning rate is just a scalar. And that's about it. Then we just log things like the losses and the parameter, and that's about it. And usually it's gonna convert very well to a super small loss in that case. And you should have this value that you can check online if it's correct, the gravitation value of the moon. And some little plots. And zoom a bit. Yes. So this is the loss function. This looks like a beautiful loss function. This is what you want to see. Always plot your loss function. Always check if there are some weird instabilities, like things going up and down. This is not correct. Try to have something very smooth. And usually reducing the learning rate helps a lot. And this is the loss, and this is G, and you see converging it nicely to the value. And you can start with whatever value, it will always nicely go there. And yeah. Here we can also see wait, on this one. Oh, I have to rerun everything. Let's rerun everything. Up, I just retrained it. It's really fast. Huh? It's a super small program. So on the CPU like this, it's insanely fast. And yeah, here's the data. It looks beautiful. The model and the data, I gotta say, it looks pretty good. And that's about it. So if you have time, maybe more tonight, if you're feeling brave, there is an exercise 2, which is very similar. Same equation. The difficulty is that you will work on a bit more complicated model, so not just a quadratic function. Exercise 2 is here. Yeah, the goal would be kind of to do this clustering example that you saw on the slides, where we have this Gaussian. Here we just fit one Gaussian and a 1D Gaussian, so it's simplified, but you still have a few parameters. You have the mean and the standard deviation. So now we're starting to work with vectors for the parameters, not just one value. And we have a bit more data. So it's just scaling up exercise 1. So it's a nice practice if you can solve this one, but then it's always the same. That's about it. Do you have any question on Zoom, whatever, before we go to the next step? Okay. So next step is gonna be a bit more chill. We're gonna work on this video study. I'm gonna post this on Slack. So Andrej Karpathy is this very famous scientist, work at OpenAI and Tesla, and he's also, he's very famous, and he is also a great educator, and he has so many great videos on deep learning. I really, really recommend to check them. He usually develops a lot of things. He do like some kind of live coding where he's gonna redevelop something live, and it's really so great to learn really how things work instead of the more theoretical lecture. And this one in particular is building this backpropagation engine. So basically what you've done by hand, pen and paper, doing some kind of software that can do it by itself. And this is kind of like a first version of the PyTorch library we're gonna try and use. So you can just, I guess we all have a laptop. So ideally you all have like some earbuds or something to watch it on your own. So everyone can just watch it at their own pace. If you don't, just maybe go on the room next door. And what we're gonna do is just regularly we'll have some checkpoints, maybe every 20 minutes or something. So we all see that everyone understands what's happening. We can discuss a bit what was on the video. And yeah, that's gonna be the whole afternoon. And then John Draper is coming. Okay, so just a little checkpoint. It's gonna be fast. Sorry for the back and forth with the other room. Just so everyone is around, I would say 10 minutes, 10, 12 something minutes. So you had like the intro of the video. Do you understand what is micrograd at this point? Like what is the high level goal of micrograds that is trying to develop in this video?
To basically teach you how neural network work at the fundamental level.
Mm-hmm. But specifically, micrograd is solving one very specific goal. Do you understand that, and how maybe it relates to exercise 1 we did this morning?
Optimization.
Yeah, optimization.
Calculating the gradient.
Yes. Calculating the gradients and basically calculating the gradient automatically. The high level goal is you give any expression and you find the gradient with respect to any of the parameters or the variables in the expression. So at this point in the video, you might see something like this, where it looks like very trivial. If you've done some Python, you're like, this is completely useless. Python already has an engine to do those calculations, and it works well. Why are we developing all of this? And you will dig into all of that with him. But the idea is that Python is not keeping track of all of the gradients. It's just going to compute the values we want to compute the gradients, it's backward pass, he's gonna explain more. And indeed, then we'll be able to have these guys automatically. That's it. We'll check a bit later, 20, 30 minutes. Well, let's see. Let's see. I don't remember exactly what's happening at 32, but at this point you should have a general idea of how micrograd works. So what's the general framework of micrograd? What's the core concept of how we can do this whole automatic gradients?
It seems like it's keeping track of what's happening at like every single step, keeping like as many of the variables as, as much information as you can towards the end, and then just kind of like checking, using that information to like check back what you finished it.
Yes. The core concept is really to break down all of this into very, very modular components, like atomic operations. And so what's the data structure, in a sense, of this whole graph? Well, I just said it. A graph. The computation graph is really the keyword here. And each node is this like modular operation. That's good to keep track of. So guys, I think you're all starting to check into the gradient step, how it's like doing the automatic gradient at this point. I think, yeah, you should. So we might not finish the video today. You might have to keep on this after John Jumper and at your own pace. Yeah, he's coming in 2 hours. Let's see. Has anyone seen the part there where they really explain how you do this computation of the graph and especially the gradient, like the backward step?
It's like calculating for every step, it's calculating like the derivative, like using like some sort of path propagation from the last value, and it's using the derivative of the last value in every step.
Yes. So I guess you'll see more later in the video, but as a little teaser, indeed, it's a very local operation. You compute the graph of a node with respect to just the node before in the computation graph. And the chain rule is going to be the important ingredient in this whole operation, because then you can just multiply the gradients at each, between each node, and it's going to give you the whole expression, because we want the gradient with respect to the very last output, which is usually your last function. I think I'm just going to let you work a bit. Yeah, at least an hour and a half, and we'll kind of discuss a bit more how the gradient works and do a little example of a computation graph with its gradients on the whiteboard. And yeah. Well done for those who are still here. We're gonna do little checkpoints to see where everyone is at. And then John will be here
We're definitely at the age of like the information.
to talk with us.
And another thing, like one agent that you can talk to 24/7 is like he's even helping you like figure out where the is. And it's formatting it even like in language that you understand.
Yeah.
As in like
Human interpretable.
Yeah, exactly.
The cold pizza. Fancy.
Right.
Will work pretty well.
Yeah, it's just working at getting you closer.
Okay, so everyone has done like maybe 1 hour and a half, at least 2 hours of video, and you'll have a bit of time after done to finish it. So at this point, you should all have something. We should all have seen like the gradient part. So how does it compute the gradients throughout the whole graph? And can someone do like a quick explanation of what's the principle? How is it doing it? And why does it mean, like, why do we use the word backpropagation at this point? Question, I don't know. We talked a bit about this at the last sequence. So what's the key principle of this framework and how do we use it to compute the gradients for the whole graph? Remember, we have this computation graph. the key point is that we can do forward pass, so we can just compute regular expression like Python does. But we also keep track of all of the operation as a graph. And that's very convenient because the gradients is usually a very modular operation. You can compute gradients at each step and assembles. The key operation here, the key property is the chain rule. It's something you have to keep in mind. So when you compute gradients at different operations, you can easily combine them to get a gradient of very, very complicated expressions. That's why we keep we store the whole computation graph. Python does not do that. This is a lot of memory to compute all of this and to keep it in the memory. Maybe let's do computation graph together. That will be one of the last gradient we do by hands as we move to more high-level frameworks. Yeah, we could do like a simple loss function. It's not going to be very realistic, but imagine we have a super simple model that just multiplies two parameters, A and B. And we compare this with the difference, the ground truth. So the prediction, this is a common way to mark a prediction, would be maybe just A times B, like nonsensical, but just bear with me. And we have some ground truth. And your loss is maybe just going to be A minus Y, which is actually a very bad loss. But let's keep it simple for now. Anyone is feeling brave enough to write a computation graph? So we have like the different numbers and the different operation in a graph to arrive at the loss function. So this is the output. This is inputs. And we have a few operations in between. Who is brave enough to try it? It's actually not super hard. Just like the three operations.
So,
do you want to try? Come on. So basically you have values and operations that all have their own boxes.
Every time.
Yeah. So maybe you could store this as an intermediary variable. That's why I called it y. So that's great to keep the multiplication, but you can store this as a square box.
What do you mean? Like,
so A times B is gonna give you y.
Y hat, okay.
Nice.
Just the loss, right?
Yes. And we just need one less value that's gonna come on the side.
One less value?
Yes.
Oh,
we
y.
have A, B, yeah, we need Y also, the ground truth.
Oh, okay. So how should I write it? Here?
So the same way that here you had two numbers that were inputs as the operator, here for your operator minus, you will need two numbers. Y hats and Y.
Y hat and Y.
Should be the gradients.
So gradient is gonna come after. For now, we just do the forward pass. So an operator usually needs two numbers, and this one is comparing.
Oh, so I need right here?
Yes,
One
you can
more?
do
Okay,
that.
okay.
Exactly. So what we could do, this is really good to make it more explicit. We could keep just something like this and maybe do -1 here, or like do y multiplied by -1 and the plus. So here we really see what is the order of differentiation. Thanks a lot. Very volunteer. And now we need to do the backward pass. And it's not too hard here. I think you remember how did he initialize the graph for the backward pass? Because it's all multiplication,
Okay,
but you start with a number. Yeah.
Yeah, you always assume that the L is having a gradient of 1.
Yes, and actually not just an assumption, it makes a lot of sense because a gradient of value with respect to the same value is always 1. So can you see when I write like this? Not so much. Well, let me move your graph, sorry. But basically, look at back. Have you see better here? Maybe you can go put this up, maybe here or something. So this is always 1, whatever L is, whatever function we are dealing with. Nice. And then, what is the goal here? The parameters are A and B. So what is the gradient that we're going to have in if L is a loss function?
So gradients of which one? Right.
We need 2 gradients here. Which one? What are the gradients? I don't need the expression right now. I just want to know what in general.
Then why?
The gradient of what with respect to what?
Gradients of L with respect to y.
Gradient of L with respect to?
Respect to A and B.
We're gonna need it at some point, but what the ultimate goal is actually for A and B, because here it's kind of the model, right? It's a weird model, but okay. And if we have the gradient of L with respect to A and B, then we can do gradient descent on them. Now there are a few steps in between, and this is where the keeping the graph is very handy here. Because before doing that, we can compute this intermediary variable. Do these 2 ones. Yeah, you can stop breaking, by the way. So don't be shy. But yeah, this is kind of the intermediate variables. And I don't know if it was super clear in the video, but there is a nice property of the chain rule that makes a lot of sense, is that you can kind of decompose any complex gradient that you have into multiples, like a chain of a multiplication. And it's like a very nice property. So does this make sense? It's just like fraction manipulation. So those 2 guys cancel out and you still have the gradient. But now you can do like individual gradients computation. So what is the gradient of L with respect to y hat? Y hat is very close to L. It's just an addition to the simplest gradient. So what is gradient of L with respect to y hat?
Multiply 1 by.
So just this part. You can also kind of cheat and just look at the original expression.
It would be
If you just look at this expression, what would it be? What is the gradient of L with respect to y hat? It's just 1 indeed. Yes. We don't even need to look at AD for now, because the key properties, we just look locally at the gradients. There is no complexity with AD yet. So this can be computed super easily. And the way he programmed the micrograph is that the addition here is the simplest gradients, where you simply, you know that the gradient is going to be, you can stay here.
It's fine. Can you go back in like 10 minutes?
Oh, 5 minutes is fine.
Yeah, we'll run outside.
Okay.
So it's taking it one step at a time, or like a step is defined essentially by like square to square?
Yes, but each operation you can manually say what's gonna be the gradient. It's always super simple rule. So the addition is gonna be 1. The multiplication is gonna be the coefficient of multiplication. The power is other rules. So you only have like super simple rules. What's the gradient now of y hat with respect to a? So y hat with respect to a. It's b, yes. And you can cheat and just look at this and do the gradient L with respect to a, which is always b. Or you can remember how we presented it in the video. And the video is just saying, oh, when I had this multiplication operation, I just look at what is the multiplication coefficient. So that's something you can hard code in the programs. And so indeed, this is just, in that case, we could have computed it just by hand very easily, but now there is a way to do it on the computer. And the same way here, we have gradient L with respect to b is a. And that's it. Pretty easy. Once you know the chain rules and all. Any question in general? I'm gonna keep going over the video and gonna make more sense
You
too.
really have to learn every single code you wrote in this presentation, because I feel like it's a lot.
There's a lot of codes. You actually don't need to build your own autograd engine. It's gonna be kind of the last time, and for many people, they never actually even do this step. Like this day is like kind of a special day in the classic deep learning courses. Most people jump directly to the high-level frameworks, and they have something like PyTorch that directly gives them everything. Here is kind of special, so enjoy this last moments where you can actually touch gradients with your own hands, because this is over. This is good to keep in mind what's happening. The last question I have for you. These are super simple operations, but you can actually build a model in Python where you have like the whole freedom of Python. You can do anything. Like Python can do so many operations. Like imagine complex operation with a complex object, maybe loading a file and concatenating files. These complex operations are not really supported by PyTorch. Do you have in mind what kind of operations are supported and what kind of operations are not supported? Because when you build a model, you're gonna have to keep this in mind. You can't do like some crazy things in your model. Otherwise, PyTorch is not gonna be able to construct this computation graph. So do you have a bit in mind where is kind of the threshold between doable and not doable? I mean, let's just list a few operations that are feasible. Addition, multiplication, powers, and then exponents, polynomials. What kind of functions? A lot of function basically. You presented 10H in the video. What kind of function basically can be used?
Is it linear?
Not necessarily linear, because the quadratic function is not linear, but it's a nice smooth function. Yes?
Continuous.
Continuous is important. Yes. Yes?
Just have a question, do the dimensions matter? Cause if like you're trying to rotate something, like if you're working with like data that isn't numbers, that should in theory also be supported, right?
Yes, but that's a good question. How do we represent any complex object into this kind of tensor format? Because here, you can just put this as a vector, and this might be just the 2 first pixels of an image, and you might have actually a giant image that you just unroll as a long vector. And there are many tricks to embed any complex objects into this vector representation. But now we want to keep with the operations. So what kind of function are supported? So Casper mentioned continuous function, and actually, I think it's basically the right answer for PyTorch. If you go to calculus class, they would probably say you have to be differentiable. So they might say the function absolutes of x is technically non-differentiable. So you have this x, f of x, and this is absolute of x. Technically, this is non-differentiable because here you have a nice slope that is constant of 1. This is like -1. And here the slope is not defined at 0. So this can be anything. In practice, PyTorch allows you to do it because numerically you never reach exactly the point 0, like it's very rare, and you can just handle it for this special case. So PyTorch very often is a bit smarter than the classic calculus. So you can try it, but there are some operations that are going to be complicated. For example, else-if statements in PyTorch. You could say, for example, your model, if your model is like more than 5, imagine your model just outputs a value between -1 and 1. And you could say, if the model outputs a positive value, it's a cat. If it outputs a negative value, it's a dog. And you might put this if-else statement in Python. Well, that's non-differentiable. That's not continuous. That's a very weird function. PyTorch is going to have trouble with that. So this is why it's important to have this day where you really remember that all of what PyTorch is doing is building this computation graph. And you have to keep in mind those continuous and differentiable functions that are the building blocks. And you can't just put anything in your model. That's about it. Maybe one question.
So you want just it's clear for everyone. So you want every single function to be differentiable, because otherwise you cannot compute the back propagation graph.
Exactly. If you have very weird statements, well, there might be no gradients of this. And you might have like, at some points, the gradient just cannot flow.
And so is there like, maybe do you want to pick some specific functions that are easier to differentiate so the backpropagation is faster? Is that...
What are you referring to? Yes, so Eve is referring to the fact that most layers are built as linear layers, so matrix multiplications. And Pierre is going to present a lot of architecture tomorrow, and you'll see it's just always the same kind of layers, but arranged a bit differently. So they're nicely differentiable, but they're also very efficient to compute. There are a lot of other things that we keep in mind. That's also why, for example, the dan function that he presented, it's beautiful, it's very smooth, but it's also kind of expensive to run, and now people just don't use it. Just moved on. The dan edge. So we have other activation functions that are a bit more efficient.
Motivation for making it.
Yeah.
I have another question. So like, does this then always assume one-to-one relationship between things?
What do you mean?
Like, because if you have to draw a graph like that one, like, well, I guess you can connect multiple nodes. Like you can have multiple errors coming out of a single node.
Yeah.
But like thinking of like biological systems don't necessarily follow strict one-to-one relationship between things. Like one thing can happen and then the following thing can be like it can be multiple different things. So like I'm just wondering how that would happen in a neural network where like every relationship is assumed to always be true. Does that make sense?
At this point, the model we work with here are super abstract, and it's sometimes difficult to connect with them with like some reality, some like more intuitive physical models. And so when John Jumper is an expert in that, he's definitely taking a lot of inspiration from how biology works to craft his architecture. But at the same time, usually the low-level layers of operation are still like those very simple and very abstract operations that have very little connection with how your real problem works. It's kind of great because the tool we use, you just apply them to any application. Very impressive. But sometimes it's very hard to interpret them.
That makes sense.